Hey everybody, and welcome to your fifth lecture in Historical Geology. This is Professor Hurt, and today we're going to be talking about igneous rocks. So we're moving right along. We've gone past kind of our introductory material on the nature of science and the metric system, geography. We've done minerals now, and now we're going to be starting to look at rocks. So we're going to look at the three different rock types in this class. Kind of the first half of this class is actually just kind of a breeze through our intro to geology class, our physical geology class. So if you've taken that class already, you'll notice that this is a lot of review. But most of you have not taken that class. So most of you this is going to be new material for you. So we are talking about igneous rocks first, then we're going to move on to sedimentary, and then there's going to be metamorphic rocks. And so we're going to talk a little bit about each of those. Igneous rocks, it's very important. Sedimentary is probably the most important, and metamorphic is kind of we only touch on a little bit in this class, but you need to know your rock types big time for this class. So it's an important lecture, and you should pay careful attention. So without further ado, I'll get started here. So I start off with this slide that always kind of makes me laugh. This is a kind of actually famous place in Hawaii, which this bus got covered with basalt. One of my students said this was Miss Frizzle's last ride, if you ever remember that Magic School Bus show. So I don't know if people still watch that anymore, but it was popular when I was a kid. So anyway, remember that all rocks are formed out of minerals. All minerals are formed out of bonds, right? So atoms and bonded atoms, mostly ionic bonds. So the minerals are held together. The atoms of the minerals are held together by different kinds of bonds. Mostly the most important type is ionic bonds. So that's where you have a plus charge atom with a negatively charged atom. Those are called ions. A positively charged atom is a cation. A negatively charged atom is an anion, and they're held together by electrostatic forces. Just like when you rub a balloon, against maybe you don't know this, but if you rub a balloon against the wall, it will stick to the wall, right? Or maybe that if you rub a balloon over your hair, your hair will start to stand up on end, sticking to the balloon. It's attracted by electrostatic forces, and the same thing is going on in the minerals, the atoms within a mineral. The atoms are sticking together, if you will, by electrostatic forces. Okay, so remember that minerals are very, very highly organized. Okay, remember there's a place for every atom and an atom in every place. So in the case of halite, which is NaCl, sodium chloride, which is rock salt, it's a chlorine, a sodium, a chlorine, a sodium, and this cubic structure. Okay, so that's kind of just a review of what minerals are like. Remember there's covalent bonds, right, that also hold some minerals together. Diamond is a very good example of a mineral that's held together by covalent bonds among carbon. You might remember too that if you have multiple minerals that are made of the same material, the same element, that those are called polymorphs. So that diamond is made of pure carbon, graphite is also made of pure carbon, and yet they are different minerals, okay, because they have different structures. Those are called polymorphs, means many forms, okay. Now the silicate tetrahedron, you might recall, is a very, very important, I can't really overemphasize what an important molecule this is, the most important molecule to geology and earth sciences. So you got to know this guy. So it consists of a silicon atom surrounded by 4 oxygens in this kind of pyramidal shape. If you can see that, it's not really a pyramid, it's actually called a tetrahedron. Tetrahedron means, tetra means 4, hedron means faces. So it's a shape with 4 faces, okay? So a pyramid has actually 5 faces, so it's different, but it kind of looks like a pyramid. So remember, you got 4 oxygens surrounding a silicon atom. This is actually an anion, polyatomic anion is the word I'm looking for, polyatomic anion. And that means it's negatively charged as a net charge of -4. So it's going to combine with different cations to form minerals. Okay, it's the most basic building block for the crust and for the mantle. Okay, it's probably 50% of any rock that you pick up or more is made up of these tetrahedra. Okay. Now remember that tetrahedra share sides, they share corners, or sorry, they don't actually share sides, they share corners. They link together in different ways. So this is what two tetrahedra look like when they are not sharing an oxygen atom. They're not linked up at all. Remember, those are the isolated tetrahedra that are common in olivine type minerals. Then you have some that are linked together. And how they are linked, that degree of silicate interconnectedness, I hope you remember, is a very, very, very important property of different silicate minerals. It determines a lot of their physical properties. You know, it determines how susceptible they are to erosion, determines how hard they are, determines all sorts of things. They're different chemical properties. So it's very important to understand about the silicate, different silicate minerals, be familiar with the different silicate minerals, and then also know how those different classes of silicate minerals are linked together. Okay, I mean physically, how the tetrahedra of those silicate minerals are linked together. You need to know that for the test. Okay, so SiO4 is the most abundant anion in the crust and mantle, the basic building blocks of the silicate minerals, and some of them share corners, some of them do not share corners, some of them share all three corners with each other, some of them only share one corner, some of them only share two corners, etc., etc. Okay. So remember, there's the 5 basic structures of the silicate molecules. Okay, there are isolated tetrahedra in which the tetrahedra are not touching, they're not sharing any oxygens. Okay, there's the single chain, those are the pyroxene types that only share one in these kind of chain-like structures. Okay, if you can see that, and you notice that the chains are not touching each other. Okay, so we also have the double chains in which we have 2 chains, but the chains themselves are connected. And you'll notice that every other tetrahedra, so if one tetrahedra will just share one oxygen, and then, or I'm sorry, actually, yeah, so some tetrahedra will share 2 oxygens. I'm sorry, 2 oxygens, and some will share 3. Okay, so that's the double chain or the amphibole type. And remember, you should be familiar with all these silicate minerals: olivine, pyroxene, amphibole. These are all be familiar to you. So mica, every single atom or every single tetrahedron shares 3 oxygens in their corners. Okay, and then the final one is the framework type silicates, quartz and feldspars, in which those tetrahedra share all of their oxygens with some other tetrahedron. Okay, so that's how those different silicate classes work. That shows how many. You'll notice how many oxygens are shared among the different tetrahedra. You'll notice that there's this increase in interconnectedness as you go from isolated tetrahedra, the olivine types, to the pyroxene types, to the amphibole types, to the mica types, to the quartz and feldspar types. Okay, so silicates, most of the rocks you see around you are based on that silicate molecule. Okay, it's very important to understand that. Granite, basalt, very different rocks, but they're both silicate rocks. Okay, they're made of silicate molecules. You should know these silicate molecules. I already went over these before. You should know them. You should know the formulas for some of these things. So quartz, SiO2, silicon, basically silicon dioxide, is a framework silicate, has a high degree of interconnectedness. So does feldspars. You'll see that there are 2 types of feldspar. This particular type is called a potassium feldspar that you see, and you see the reason that's called a potassium feldspar is because it has some degree of potassium in it. Okay, so I should actually put here K feldspar. K stands for potassium. Remember, you might remember that the symbol, elemental symbol for potassium is K. So K feldspar has some potassium in it, and it's aluminum, silicon 3, oxygen 8, and it's a framework silicate. Mica is a sheet silicate. There are 2 types. There's biotite and muscovite. Muscovite's the white mica, and biotite is the black mica. There's amphibole, which is a double chain silicate. There's pyroxene, which is a single chain silicate, and there's olivine, which has this chemical formula, either iron or magnesium 2, silicon SiO4, 1 silicate tetrahedra, to 2 cations, okay, either iron or magnesium, okay. Olivine is green, and it is very abundant in the mantle, okay. So that's how that all works, right? Rocks are made of minerals. Granite, for instance, is made of feldspar, quartz, and mica. Could be amphibole too, but to be a granite, you have to have both K feldspar, potassium feldspar, and the other kind of feldspar, which is called plagioclase, and quartz. Okay, so you have to have those 3 minerals: K feldspar, plagioclase, and quartz. And usually there's some other kind of lesser mineral, or maybe many lesser minerals that are involved in granite as well. But these are the big 3 in any granite. To be a granite, you have to have those 3 minerals in it. Absolutely. Gabbro, which is another common rock we're going to talk about, igneous rock today. It has feldspar, but this kind of feldspar is more of the plagioclase feldspar. Okay, plagioclase feldspar. And you have to have pyroxene. Okay, that's a gabbro. So we're doing igneous rocks today. Now, igneous rocks are formed from a melt. That means they're formed from melted rocks. They're basically solidified magma. That's another way of thinking of them. So we can have 2 kinds of melts, all right? We can have lava and magma, and they're different. Lava is a molten rock that erupts onto the surface, and magma is a molten rock that remains subsurface. So, only a little bit of the melt that is generated in the earth ever makes it to the surface, right? A lot of that melt just stays in the ground, and a little bit of it sometimes erupts and spews out over the countryside. But most of the melt, the great majority of melt, stays under the earth. Okay, so let's get into a little bit of classification of igneous rocks. So I just kind of want you to be aware of this. Now, if you were all taking lab classes, this is very important. But if you're not taking the lab, and most of you aren't, this is not so important. But I do want you to be aware just kind of how we classify these things, basically. So we classify igneous rocks. That means we make distinctions among the different kinds of igneous rocks. We classify them on the basis of something called texture and composition. Texture is, so you need to listen here because this is a little bit complicated. Texture is the distribution of different grain sizes in the rock, crystal sizes. Every rock is made of minerals. Every mineral is composed of, they're form crystals. Okay, minerals always form crystals, right? Because they have that crystalline structure. So the texture is describing how those minerals are distributed in terms of grain size. So are they all big grain sizes, like all big crystals, or are they all small crystals? Is there a mix? Is there maybe like a lot of small crystals, a lot of big crystals? So anyway, we're gonna classify that. That's called texture, and that's how we're gonna classify igneous rocks. We're also gonna classify them on the basis of composition. That's what the rock is made of in terms of elements. Okay, so these are the 2 main types of texture that you should absolutely know. Okay, those are fine-grained and coarse-grained. Okay, so fine-grained and coarse-grained. Fine-grained means most crystals are microscopic. So if you look at this basalt, for instance, can you make out like the individual crystals, or does it just look like a homogeneous plain black rock? So hopefully you can see this looks like a homogeneous plain black rock. You can't actually make out the different crystals in the structure. Okay, granite is a coarse-grained rock. Okay, you can actually make out the shapes of the different crystals there. Do you all see that? These are all different crystals of different minerals. The mineral I'm circling is potassium feldspar. Okay, that's potassium feldspar. The white mineral that you see here is the plagioclase feldspar. And the grayish mineral that you see here, I'm outlining here, is quartz. Okay, remember you have to have quartz, potassium feldspar, and plagioclase to be a granite. The black stuff is probably either mica or amphibole or a mix of both. So fine-grained igneous rocks, The reason that we make this distinction on texture is because it tells us, the texture tells us how the rock formed. Okay? Fine-grained igneous rocks crystallized from a lava. That means that they erupted, they are volcanic rocks, they erupted on the surface. Another term we use for this is extrusive. So fine-grained, volcanic, extrusive, they all kind of mean the same thing. Okay? So you want to be familiar with all those different terms. On the other hand, a rock that is an igneous rock that is coarse-grained is plutonic or intrusive. That means that it formed as a magma chamber below the surface. So these are the plutonic rocks in the magma chamber below the surface. These are the volcanic rocks that erupt on the surface. Okay? So this outcrop of granite that you see right here, if you can believe this, this is true, this was a magma chamber. Whenever you find granite in real life, know that it was a magma chamber. It was deep below, sometimes maybe 10 kilometers below the surface of the earth. It was very, very deep at one time below the surface. But tectonics, erosion have brought that magma body to the surface and exposed it. And we have it now today, in all these different exposures. You can find granite all over the place. It used to be deep, but now it has been brought to the surface and we can look at it, see it, touch it, feel it. And those are plutonic rocks. They're intrusive rocks. Okay. Now, 4 other useful textural terms you should be familiar with. One is porphyritic. So porphyritic means that most crystals are microscopic, but there are some large crystals. Porphyritic textures are volcanic textures. Okay, so this is volcanic. And in fact, I'll just tell you right now that all 4 of these are all, I should really say, useful volcanic textural terms. All these are volcanic. Okay, this is all volcanic textural terms. So none of these are coarse-grained, plutonic, intrusive rocks. These are all volcanic rocks, okay? Porphyritic textures, microscopic with some very large crystals. Vesicular means you have a lot of fine grain, a lot of vesicles, which are like bubbles or little holes in the rock. Glassy is like obsidian. It's made of volcanic glass that was a fast cooling, usually very high silica melt that did not have time to crystallize fully, and so it contains a lot of glass. Pyroclastic is a rock made out of volcanic ash. Okay, usually it's a mishmash of different broken crystal rocks that maybe the ash flow picked up, but mostly all held together with ash. Okay. Here's a porphyritic texture. You can see that there are a few large crystals, but it's mostly in a fine-grained ground mass. You can see that this stuff is fine-grained, right? So I'll put FG for fine-grained ground mass, but a few crystals, larger crystals held in that ground mass. That is a volcanic texture. This is a vesicular texture. You can see all the little holes, okay? All those little holes are created by gases trying to escape the lava. Lava isn't just melted rock. It is melted rock mixed often with water and carbon dioxide that's kind of held, just like carbon dioxide is dissolved into like a soda when it's in its 2-liter bottle or in its can, So you open up a 2-liter bottle of Dr. Pepper or whatever, and when you undo the cap, you release the pressure, all of the gases start to come out, okay? Because the gas was dissolved in the liquid under pressure. Well, guess what? Rocks, when they melt, when there's water in them and carbon dioxide and sulfur and all these different gases are in them, and they're under pressure, all those gases are dissolved in the melt, and when they erupt, they release those gases. So it creates all these little vesicles that were filled with volcanic gas, okay? And the volcanic gas escaped. This is obsidian. It has a glassy texture. It's actually volcanic glass. So that's forms when you have very fast cooling material that's very high in silica. It can form this kind of texture. Okay, there's kind of wondering if I should watch this. It's always kind of hard to hear what is going on in this thing, but maybe if you want, you can watch this. It's kind of cool video that shows an obsidian lava flow. I kind of don't want to I just noticed it's almost impossible for me to pick up the sound on the microphone that's coming from the video. So I'm just gonna leave it for you guys to watch if you want. Now, another type of texture is called pyroclastic, and you'll notice if you look at this, probably a lot of you are looking at it and you're like, wow, that kind of looks like concrete or something, you know, like man-made concrete you would mix to make a sidewalk or something like that. Because, you know, when you make concrete, you mix cement with like rocks and sand and stuff like that. So this kind of texture, pyroclastic texture, is called a tuff. And it's basically, you know, it is kind of a little bit like concrete. You have, what happens basically, you have rocks and mineral fragments that are maybe on the side of a hill, on the side of a volcano. And as the hot ash rushes down the side of the volcano, it picks this stuff up. And here's the hot ash plume. It picks this stuff up and eventually solidifies and forms a tuff. Okay, this is just a part of a video that's pretty entertaining to watch. There's a lot of pyroclastic flow videos if you ever want to watch those on YouTube. Here's just one example of that from a volcano in Italy. So igneous rocks can have the same composition but different textures. So a good example of this is basalt and gabbro. Basalt and gabbro are identical in terms of chemical composition. So if we took these two rocks to the lab and had them look at like the chemistry and what elements are in it and how much oxygen, how much silicon, how much iron, et cetera, are in these rocks, a chemist could not determine the difference between these two. They would look exactly the same because they're made of the same liquid. But this one, the gabbro, cooled underground, and this one cooled up on the surface. Because it cooled up on the surface, it cooled quickly. And because it cooled quickly, the crystals did not have time to grow and get big. One thing that you'll learn in earth sciences and historical geology, a geology class, is that it takes a long time for crystals to grow. I don't know if you've ever grown like rock like the rock sugar kind of stuff, but you might know that it takes a long time for those crystals to grow. It takes like days, sometimes weeks, for the crystals to grow. Okay, so that's the same thing here. You know, it takes days, weeks, months, years even for crystals to grow and get big, and if it doesn't have time to grow, the crystals just remain microscopic like they do in basalt. Okay, cooled too quickly. Gabbro cooled under the earth, and because it's warm under the earth, it took them a lot longer for that stuff to cool. Okay, so which of these formed from a volcano? It was the basalt. Okay, the basalt formed from a volcano. This formed from a magma. Now, let's take a little segue and talk about how we produce melts. Okay, like where does all this lava and magma come from? So this is a very good video, but it's kind of advanced. I think if you want to kind of get a very good grasp on this subject, you can watch this. But it is a little advanced, so, or maybe a lot advanced, but it is a really good video explaining how melts form. So melts of the earth, you know, that erupt on the earth, mostly originate as melts of the mantle. Okay, so usually what happens is the mantle melts. When the mantle melts, it only partially melts. Okay, it only partially melts. So let's talk a little bit about this. This is a depiction of Earth's surface down to its center. Okay, so here's the surface. Here's depth. It goes all the way down to 6,400 kilometers. Okay, the lines that you see here, like this blue line, it says temperature. And what that represents is the temperature of the Earth as you go down through the Earth from the surface to the core. Okay, so you start off really low, right? You start off at like 25 degrees Celsius. By the time that you get down to about, this is about maybe 100, 200 degrees, or sorry, 200 kilometers down, you know, you're maybe 2,000 degrees, maybe 1,500 degrees Celsius, right? Y'all see that? So you come down here. Okay. So when you get down to the base of like the lithosphere, you know, you're about 1,500 degrees Celsius. Okay. 1,200 degrees Celsius, something like that. So you'll notice that we have this line that represents the temperature of the Earth. Okay, y'all see that. And then we have this other line that's kind of interesting, this kind of shaded region. So let me use a different color here. Let me use blue here. We have this other line here. Do y'all see this line? And there's, on the left it's shaded, on the right it's not shaded. That line represents the melting temperature of the Earth. Okay. So you'll notice that the melting temperature of the Earth, now here's the core mantle boundary right here. Okay, that's the core mantle boundary. So this is all mantle. Okay, do y'all see that? This is all mantle. Below the mantle, this is core. This is the outer core. This is the inner core. I'm going to put I core and O core. Okay. Now notice that when you get to the outer core, that the temperature of the Earth is higher than the melting temperature. What does it mean if the temperature is higher than the melting temperature? Well, it means that you're melted, right? Does that make sense? Yeah, it makes a lot of sense because the outer core we know is molten. Okay? We know it's molten. So this is molten. Okay, so that makes sense. But let's go back and focus on the mantle because we're talking about melting the mantle. Right, we're not talking about melting the core because the outer core is melted, and that material never makes it to the surface. You know, otherwise we'd have like eruptions, volcanoes of pure liquid iron. Right, so we don't have that. That material stays down there. So let's look at the mantle. The melting temperature, you'll notice, is greater than the actual temperature that's in red, the actual temperature of the mantle. So that means that the mantle is solid. However, there is this point right around here. Do y'all see that? And it's about from maybe the base of the crust, maybe 30 kilometers down, to maybe 200 to 150 kilometers down, maybe even 300 kilometers down, in which the temperature of the Earth gets very close to the melting temperature. And sometimes it does cross over, and that's when you get melt generated. Okay, so it's right there that you're going to generate melt. Okay, so most of the lava and the magma that is generated from 30 to maybe 300 kilometers down below the surface, but not deeper than that. Deeper than that, you can see that the melting temperature is way above the actual temperature. Okay, so I want to present to you three ways to melt the mantle. Okay, so think of this conceptually with this diagram. So here's a pressure temperature diagram. Pressure is on the bottom, temperature is on the vertical axis. Now you'll notice when you look at this diagram that the melting temperature is not constant. Okay, the melting temperature is actually increasing as we go down through the surface, right? So the melting temperature starts off at maybe like 1,500 degrees Celsius, and when you get to the core mantle boundary, it's really high. It's maybe 3,500 degrees Celsius. Okay, so the melting temperature increases with pressure. All right, that's a really weird concept probably for a lot of you, but it's really important for earth sciences. The temperature of melting increases with pressure. Okay, so this is the melting line. Okay, at low pressure it's low, but at high pressure it's high. Okay, so with increasing pressure it becomes harder and harder and harder to melt something. And that should make sense because when you melt something, it expands, and pressure is kind of trying to keep things condensed and contracted in low volume if it can. Okay, so on the higher temperature, on the upper side of this line, things are molten. On the lower side, it is solid. Okay, now this is our temperature here. Okay, it's the polygon here. That represents the current temperature. Now, so we're talking about ways to melt the mantle. So the idea here, the game, if you want to think of it here, is to make our polygon cross the line. Okay, right now it's on the solid side, right? The polygon's on the solid side of the melting line. We want it to cross over to the molten side. So if you think about this, there are 3 ways to do this. Okay, way number 1, how do you melt something? This is the way that everybody knows and everybody thinks of. The first way to melt something is to move it higher temperature, increase the temperature, make the temperature go up. So we move it up to cross the line. Okay. However, the way that most people, unless you're a geologist, you don't think of, a very effective way actually of melting the mantle is to move it to the left or lower the pressure. Okay, so lower pressure. So we can lower the pressure, we can raise the temperature, raise T. Those are 2 ways to melt the mantle. They totally work. So you can, if you can believe this, it's kind of hard to believe, but you can melt a rock without changing the temperature, but just lowering the pressure. Okay, that's pressure-induced melting. Another way is kind of cheating. It's to take this whole line, don't change the pressure and temperature, and take this whole line and move it. So we'll move the melting line. That's when we lower the melting temperature. Okay, so we're going to put lower MT, which is melting temperature. Okay, does that make sense? So those are the 3 ways you can melt the mantle. You can, and by the way, I just want to say this again, if you're doing something else and you're not paying attention, I know this is kind of like thick, heavy stuff. It sounds kind of dry, maybe. It's maybe doesn't sound very interesting, and it's very complicated, but it's incredibly important. It's incredibly important for all of historical geology, because we're going to be talking about how the mantle melts a lot, because it's so much of like plate tectonics and the continents and where the continents come from and where the volcanoes come from and what killed the dinosaurs and blah, 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 blah. It has to do with this stuff. So I urge you please to pay attention right now. Put away, if you're doing something else, put it away and listen up. So there are 3 ways to melt the mantle, right? Raise the temperature, lower the pressure, or move the melting line. Okay, and all 3 of those happen in real life. Okay, so temperature, raise the temperature, reduce the pressure, lower the melting temperature. Those are your 3 ways, and those happen in real life. In Hawaii, for instance, we have a hot spot in Hawaii. That's why there's so much volcanism there. It's because the temperature is relatively higher than other places. We therefore get a lot of melting and a lot of volcanoes. There are a lot of places where there's decompressional melting. So, for example, all of the volcanoes that form in California or all over California. I know there hasn't been a volcanic eruption in California recently, but there are a lot of volcanic eruptions. There have been a lot there. Those are all depressurization volcanoes. Okay, depressurization is also how we have melting at mid-ocean ridges, which we'll talk a lot about in this class. lowering the melting temperature happens at all island arc subduction zone areas. So Mount Fuji, for instance, this volcano formed by lowering the melting temperature. And actually it lowers the melting temperature by introducing water into the mantle. Okay, so I hope that makes some sense to you all. All right, so let's talk a little bit now about a very important aspect of this called Bowen's reaction series. So Bowen's reaction series is named after this petrologist. A petrologist is someone who studies rocks. Petro means rock. It's the same root as Peter, right? So you might know when Jesus went to get his apostles, you might know if you know this story, Jesus called Peter, his real name was Simon, right? Or Simon Peter. And he changed his name to Peter, Petro, the rock. Actually, his name is the rock, right? So that's what that name actually means. So he's a petrologist. So petrologists study rocks, not petroleum. So I always get that because I'm actually a petrologist. That's my actual discipline. So people always think I study oil, but I don't. But okay, so this is Bowen's reaction series. So let's talk a little bit about this. Bowen was a real famous petrologist, and he did this experiment where he just took a big vat of basalt. Okay, basalt, like let's say basalt rocks. And he turned the heat on. There's the fire. And he melted that basalt. Okay, so it became molten basalt. So he had this big thing of lava. Okay, so there's the lava in his vat. All right, now what he did is he let that basalt cool down and crystallize. And as it cooled down and crystallized, he just kind of looked at what happened and how it cooled and what minerals are formed. Okay. Now, most of us are familiar with when something is, a liquid and then it freezes and it crystallizes. We think of it as having like one melting temperature, right? We think of it as having one melting temperature. But actually, that's not reality with rocks. Rocks have they cool over a range of temperatures. Okay, so melting or freezing, crystallization will happen over a range of temperatures, and different minerals will crystallize out. And that's what Bowen discovered, is that as this basalt cooled down, different minerals formed. Okay, so this applies to magma bodies, right? If you have a body of magma, it's cooling, different crystals are going to form slowly out of that magma body. Okay, so this is how it goes. Now, it's kind of cool. Just look at this. We start off at a high temperature, and we are going to cool down slowly to a low temperature. So the temperature at which you take a basalt, the temperature at which the basalt is totally molten is around 1200 degrees Celsius. The temperature in which it is totally crystallized is about 700 degrees Celsius, and things are going to start coming out little by little. Okay, so when we start to cool things off, the first minerals to crystallize, it's olivine. Okay, so olivine will come out first. Then we let it cool down more, and we'll see pyroxene come out. Okay, and then if we let it cool down more, we'll see amphibole, and then biotite mica, and then potassium feldspar, and muscovite mica, and then quartz. Okay, so that's what we'll see in terms of the crystals coming out. Plagioclase feldspar, these are the plagioclase feldspar on this side. These are the calcium-rich feldspars. Are going to be continuously coming out, but their composition is going to change from calcium-rich to sodium-rich. So it'll go from this mineral right here, which is anarthite, which is a type of plagioclase feldspar. And slowly cool, as it gets cooler and cooler, it will start to become more sodium rich. So that whole plagioclase series, going from a calcium-rich plagioclase to a sodium-rich plagioclase, is called the continuous series of crystallization. On this side, where you have different minerals crystallizing out, this is called the discontinuous series of crystallization. Okay, so you'll notice that this order of crystals is very interesting because it's the same order that we learned about in terms of silicate interconnectedness. The olivine comes out first, it's the isolated tetrahedra, and the quartz comes out last, which is the framework tetrahedra, right? Pyroxene is the single chain, amphiboles the double chain, micas are the sheet silicates, and feldspars and quartz are the framework silicates. Okay, so it's really interesting because it kind of recapitulates that whole interconnectedness aspect of silicate crystals. Okay, so the composition goes from something called ultramafic to mafic to intermediate to felsic. Okay, these are new terms for you that I'm sure most of you have not heard of before, so let me explain them a little bit. These are the terms that we use to describe composition. The composition, okay? This is, so when I ask about composition of an igneous rock, this is what you got to know, okay? Composition. So we have ultramafic, mafic, intermediate, and felsic. So if I ever ask you for the composition of an igneous rock, you're going to use one of these terms, okay? Mafic, that word mafic comes from magnesium and ferric. Does anybody know what ferric means? Well, I can't hear your answer. I always forget I can't hear anybody's answer. So ferric means it's Latin for iron, okay? So this means magnesium and iron rich. Felsic, this term, weird term felsic, means feldspar and silica, that is silicon, so quartz, okay? Feldspar and quartz, okay? So these are going to be iron and magnesium rich minerals like olivine and pyroxene. Felsic are going to be feldspar and silica rich rocks like these ones, like granite, okay? Quartz and potassium feldspar, okay? You'll notice that plagioclase feldspar, these are the plagioclase feldspars, form in all these different compositions, okay? So Bowen's reaction series, it's really hard concept for beginning students to understand. If it seems confusing, it just takes getting used to, okay? But I think the bottom line that you want to understand is that rocks do not have a single melting temperature. They melt and they crystallize over a range of temperatures, and they're going to crystallize different minerals as they cool, okay? And in this case, those minerals are going to get more and more silica rich as you cool, and they're going to get more and more interconnected, okay? All right, so this is kind of a diagram. I'm not going to go over this necessarily too much, but it's just showing you that ultramafic rocks, you would expect a lot of olivine and pyroxene. For mafic rocks, you would expect a lot of plagioclase feldspar and a lot of pyroxene. Okay, so mafic rocks are made of plagioclase feldspar and pyroxene. Intermediate rocks are going to contain little bits of feldspar, like potassium feldspar. I'm going to put potassium feldspar here, so orthoclase feldspar. Potassium feldspar, little bit of quartz, a lot of plagioclase, right? You can see a lot of plagioclase, maybe some muscovite, maybe some biotite, maybe some amphiboles. So you see that intermediate rocks really can have a lot of different minerals in them. Felsic rocks are going to be potassium feldspar, quartz, right? A little bit of plagioclase, muscovite, biotite, and amphibole. Okay, so those are the kinds of minerals you expect in the different compositions. Because remember, these are all compositional terms: felsic, intermediate, mafic, ultramafic. Okay. So let's see. I don't know if I want to go over this stuff too much, but like the first rocks, like the rocks that are going to crystallize at a high temperature, are going to be olivine rich, right? They're going to be ultramafic. The things that are going to crystallize at a slightly lower temperature, let's say 900 degrees Celsius, are going to be like mafic. And things that are crystallizing at like 600 degrees Celsius are going to be maybe like feldspar rich. They're going to be more intermediate. Okay, so we really do see this in real life. So, for example, if you go to the Palisades, in New York, along the Hudson River Valley, there's these beautiful Palisades, and this is literally a big magma body of basalt that cooled slowly, and literally you see Bowen's reaction series played out. If you go to the lower part of these Palisades, you'll find olivine, and you go up higher, you find feldspar, especially plage feldspar, right? I'm going to put plagioclase, plage, feldspar, and pyroxene, and towards the upper part, you find more potassium feldspar. So you literally see Bowen's reaction series played out here. Okay, and we'll talk about the formation of the Hudson River Valley Palisades later in this class. Okay, so again, let's go back to compositional terms here. Mafic, remember, means magnesium and ferric iron. Okay, refers to magnesium iron-rich rocks. These have, now this is what you want to know. These have low silica. They contain mostly pyroxene, plage feldspar, plagioclase feldspar, and olivine. They are the first silicates to crystallize out of a cooling basalt. They are high melting temperature, and they are low viscosity. And the low viscosity means that they are very fluid. They flow easily. Okay? That makes more fluidic magma. That is, and also, by the way, makes gentler eruptions. So I know it's weird to think of an eruption as gentle, but they are kind of gentle. Okay, Hawaiian eruptions are relatively gentle. They don't explode. Like, did you ever notice how when there's eruptions in Hawaii, they don't have these huge plumes of ash? Okay, they're not explosive. That's why. Felsic composition, on the other hand, is high in silica. Felsic means feldspar and silica. They are rich in feldspar and quartz, potassium feldspar especially. The last silicates to crystallize out. They have a low melting temperature, and they have an extremely high viscosity. Extremely high. And it makes very sticky, viscous magma, very slow moving. And because it's so slow moving and so difficult to mobilize it, these make very explosive eruptions. So Yellowstone, for instance, you might be familiar with Yellowstone, is a supervolcano. Someday it will erupt again. It could erupt again tomorrow. It could erupt again in 50,000 years. But it'll erupt again. And when it does, it's a huge, devastating eruption. Yellowstone is literally, like Yellowstone National Park, is literally sitting in a crater 18 miles across of the last eruption. So it's a huge crater. You can imagine the magnitude of that eruption. It's extremely explosive. If Hawaii was explosive like Yellowstone, the whole island would just be blown apart. Okay, it's tremendous. Now, intermediate is another compositional term that just means intermediate. It means medium between mafic and felsic. Okay, so these are rich in feldspars. In fact, they're almost entirely made of feldspar, plagioclase feldspar especially. I mean, when you get a intermediate rock, it's sometimes it's like 75%, 80% just plagioclase feldspar. They are intermediate in silica concentration. They have an explosive eruptive style, and they're intermediate in their viscosity. Okay, Mount St. Helen, which was the last big eruption in America, was a intermediate eruption. All right, so let's look at this chart. You have to know these 6 igneous rocks. So this is something you just need to memorize, okay? Because it'll be on the test. It'll probably be on the final exam. You just need to know this, okay? So there are 6 rocks shown here. On the left are the fine-grained. Remember, we classify igneous rocks by texture and composition. So on the left are the fine-grained rocks. That's the fine-grained texture. On the right are the coarse-grained rocks. Okay, so the slow-cooling, coarse-grained rocks on the right, fast-cooling, fine-grained rocks on the left. And we're going, in terms of composition, we're going from mafic on the bottom to increasing silica content, felsic on the top. Okay, so rhyolite, a rock called rhyolite is your felsic fine-grained rock. Granite is your felsic coarse-grained rock. Andesite is your intermediate fine-grained rock. Diorite is your coarse-grained intermediate rock. Basalt is your mafic fine-grained rock. Gabbro is your mafic coarse-grained rock. Okay? So gabbros and basalts are mafic. That means they're going to have a lot of pyroxene. And you can see this line passes through. They're going to have some olivine. They're going to have some plagioclase. Okay? Your intermediate rocks are going to be mostly plagioclase. But they might have a little pyroxene. They might have a little mica. They might have some amphibole. In fact, they probably will have amphibole. Your felsic rocks are going to be so potassium feldspar. I'm going to call this potassium feldspar instead of orthoclase feldspar, but you should know that they're roughly the same. It's going to have quartz, it's going to have plagioclase feldspar, and it's going to have some mica and some amphibole in it. Okay? So you should know what minerals are common in the different compositions: felsic, intermediate, mafic, ultramafic. You should know these 6 rocks: rhyolite, granite, andesite, diorite, basalt, gabbro. If I ask you on the test, which I will, something like, what is a fine-grained mafic rock, you should know that's basalt. If I ask you, what's a fine-grained felsic rock, you should know that's rhyolite. Okay. If I ask you, what's a coarse-grained felsic rock, you should know it's granite, etc., etc., etc. Okay. You should know those 6 rocks. You should know that they're coarse-grained, fine-grained, and whether they're felsic, intermediate, or mafic. Okay. So there you go. There's just a close-up to kind of give you an idea what these rocks look like. There's the rhyolite, the granite. You can see that they're often kind of pink from the potassium feldspar. Your andesites and diorite, these are the intermediate rocks. You'll see that they're kind of salt and pepper, gray and salt and pepper colored. And then here's your basalt and gabbro. You'll notice they're dark colored from all the pyroxene. Okay, pyroxene is a very black mineral. These are just some other rocks that are based off of textural terms. So obsidian is volcanic glass. Tuff is pyroclastic flow. It forms from the ash from a volcano. Pumice is kind of the volcanic frothy ash that contains a lot of air. You know, sometimes pumice floats in water. It's so light. It's a volcanic rock, though. And scoria, which is a vesicular basalt. So it's a basalt that has a lot of vesicles, a lot of bubbles from all of the volatile gases and components that were in it. So, to kind of review what we talked about today. Melts in the mantle can be generated by decompression, lowering the pressure, or by raising the temperature, but they can also be generated by lowering the melting temperature, i.e. adding a flux. A flux is a very important word. Flux is a thing that lowers melting temperature. So for example, some of you might know, if you've ever lived in a cold place where the roads ice up, that sometimes the city will salt the roads to remove the ice. Okay, and you might know that in really cold places you could buy bags of ice. You go out and salt your driveways or salt your sidewalks or something like that so that they don't ice up. That salt is a flux. The salt, how does salt melt ice? Does it lower the temperature or does it lower the pressure of the ice? No. Does it raise the temperature of the ice? No. What it does is it changes its composition and lowers its melting temperature, and that's how it melts the ice. It's a flux. So salt is a flux for ice. Okay, it lowers the melting temperature of ice. Water is a powerful flux for the mantle. It lowers the melting temperature of the mantle, and it generates magmas in the mantle. So that's that kind of melting, called flux melting. Now, minerals crystallize according to Bowen's reaction series. High temperature minerals you'll crystallize out olivine, pyroxene in this order down to quartz. On the continuous side, you're going to start off with more calcium-rich plagioclase, and the plagioclase will gradually become richer and richer in sodium. Okay. You should know all these felsic, intermediate, mafic, ultramafic terms. You should know what rocks. You should know all these rocks here. I didn't mention peridotite, but peridotite's the ultramafic rock. It's an ultramafic, coarse-grained rock. Now, you should know what the terms mafic and felsic mean. You should know that felsic is high in silica, mafic low in silica. The mafic rocks are denser, richer in magnesium and iron. Felsic are richer in silica, richer in sodium and potassium and aluminum, and they're poor in Mg and Fe. That means magnesium and iron. They're more light colored. These are more darkly colored. These are denser. These are lighter. These are, they have less density. So you should know all those differences I just mentioned, okay? I'll be asking about those kinds of things on the test, okay? And there's a lot of information. You can see how complicated all this is. So it would really behoove you to go and read your book and read this chapter on igneous rocks, okay? Because there's a lot to it, and you need to know it. So intrusive rocks. Remember, rocks that form igneous rocks that form underground. They are slow cooling and coarse. Ooh, that's a misspelling. Coarse. Spell coarse like that with an A. Coarse grained. Extrusive igneous rocks are rapid cooling. They're fine grained. Those are the volcanic rocks. Okay. Another term for this coarse grained rocks is plutonic. Plutonic comes from the root Pluto, is god of the underworld. Fine grained is volcanic. So, sorry, I was just drinking my coffee here. So you want to memorize these 6 rocks. You want to know these felsic, intermediate, mafic terms. I'm trying to see if there's anything else you need to know. You should know that mafic lavas are higher melting temperature, low viscosity, gentle eruptions. Felsic lavas are low melting temperature, high viscosity, and explosive eruptions. Okay, you should know all that. And that's it. So, like I said, there's just a lot of information here. You should really read your book. And it's good for you to get information in multiple ways. So not just lecture, but also reading and studying. So anyway, I'm going to end here. That's a lot of information, so you got to study hard for this material. And I'm going to sign off here. And good luck on your lecture assignment. And let me know if you have any questions. Okay, so I'm going to. Whoops, I'm trying to pause this here. Okay. All right, so take care and have a good weekend.